Hello friends, subscribers and new viewers of this rapidly growing channel. In this tutorial, we explain how to write a disciplined and object-oriented C++ code for interfacing Arduino or ESP32 microcontrollers with low-cost Hall effect encoders. Over here, you can see our motor with the encoder. Here is the encoder, and here is a DC motor. The DC motor contains a gearbox, and behind is the Hall effect encoder. As I'm rotating the main shaft of my DC motor, over here on the computer screen you can see the detected pulses. The pulses are detected by using Arduino, in particular Arduino Mega, and a C++ code I wrote. For example, if I rotate for 2 times 360 degrees, I will be back to 0. And the pulses are 0. Then again, if I rotate for 360 degrees, you'll see that the pulse number is around 300 something. And if I go back, I will go back to 0. The detected pulses can easily be converted to the angle of rotation. Moreover, by measuring the interval between two pulses, you can also obtain the angular velocity. Let us first explain the main motivation for creating this video tutorial. In my previous video tutorial, whose link is given in the description below this video, I explained how to write unstructured C Arduino code for interfacing encoder with my Arduino. However, this is a naive approach for writing an interface. It leads to a cumbersome and unreadable code that is difficult to debug and that is difficult to interpret. Namely, if you want to integrate an encoder in a complex project involving a number of sensors and actuators, you need to learn how to write a structured and object-oriented C++ code. In this tutorial, we will teach you precisely that. That is, I will teach you how to write reusable, disciplined, and structured C++ code for interfacing encoders. As you will see later on, the main challenge was how to properly write a C++ class that will properly set the interrupt functions necessary to interface the encoders. In the next several video tutorials, we will explain how to use the code developed in this video tutorial to develop a complete servo control system for DC motors. Over here you can see the Arduino and C++ code that interfaces the encoder with Arduino. In this tutorial, I will teach you how to write this header file. This header file defines a class that embeds all the functions that you need to have in order to interface your microcontroller with the encoder. Then I will teach you how to write this implementation file that precisely implements all the functions. Then I will teach you how to use the defined class in this simple Arduino code that will define the encoder interface, initialize several variables, and read the data or read the pulses that are recorded by the encoder. And over here you can see the readings, and if I rotate the main shaft you can see how the pulses are being detected and how they're being changed in real time. What is important about this code is that all the complexity is being embedded inside of the header and the implementation files. And you can simply use the developed class. That is, you define over here the encoder object, over here you initialize, and over here you read the data. Literally 3 lines of code. In my previous tutorial, I explained how to place everything in a single code, and the code will be 50 or 60 code lines. Now imagine that you have several encoders plus several motors and additional sensors, and if you embed everything in a single file, the code will be completely unreadable and difficult to debug. That's why a better practice is to embed everything inside of a header and implementation files and simply to use it by calling the objects, defining and initializing. In this way you can define an object-oriented and structured code that's easy to use, easy to reuse, and easy to debug. And this is a standard practice in robotics and control engineering. That is, I will teach you standard practices and methods that professional engineers are using. Before I start with explanations, I need to mention the following. I developed a detailed manual containing a wiring diagram, then containing basic information on how to interface an encoder with Arduino, explaining the basic principles of detecting pulses and how the detected pulses can be used to develop the code. In addition to this, I also developed two files, the header files and the implementation file. Links to this manual as well as to all the files explained in this video tutorial are given in the description below this video. First, we start with basic information and with the wiring diagram. We are using a low-cost DC motor with an integrated Hall effect sensor. There are a number of versions and designs of a DC motor and an encoder. You can find these motors on Amazon, eBay, DigiKey, and similar online stores. In particular, in this tutorial, we are using a low-cost motor with the product name GA37520 with AB phase incremental Hall encoder. Since this is a low-cost product that does not come with a detailed document describing the specifications of the encoder, we only have basic information about this encoder. The main thing is the wiring diagram that we will explain over here. All other parameters can be experimentally determined, and we will explain this later on in this video tutorial. Here is the wiring diagram for our encoder. Namely, if you turn back side of the motor, you will see the encoder and you will see this connector over here. This connector has 1, 2, 3, 4, 5, 6 wires. The first wire is the motor plus. The second wire is the encoder ground. The third wire is C1 encoder. This is the output phase A of the encoder. The fourth wire is the C2 encoder. That is the output phase B of the encoder. Then this wire, that is the fifth wire, is the encoder power, and the last wire is motor minus. In this video tutorial, we are using these four wires. That is encoder ground, output phase A, output phase B, and the encoder power. Over here you can see the Arduino wiring diagram. So let's analyze this diagram. Encoder phase A, or this wire over here, should be connected to the Arduino pin number 2. And you should be very careful about selection of this pin. Namely, in the case of my board, that is in the case of Arduino Mega 2560, this pin 2 is the interrupt pin. And it's very important to connect phase A to the interrupt pin. In the case of this board, other interrupt pins are 2, 3, 18, 19, 20, and 21. That is, you can connect phase A to any of the interrupt pins. In the case of other Arduino boards, such as Arduino Uno, you need to look online and to find the interrupt pins. I think that pin number 2 in case of Arduino Uno is also the interrupt pin. Then, the encoder phase B, or this wire over here, that is the fourth wire, should be connected to the pin 7 or to any digital output pin. That is, to any pin where you can send or read high or low voltages. I have to correct myself. Here I need to say digital read pin. This is very important. But digital read and digital send or digital input and output are actually the same. It's just a matter of fact how you configure your Arduino to work. Then over here, you need to connect the encoder power to Arduino 5 volts. That is, this wire over here, encoder power, should be connected to Arduino 5 volts. And finally, you need to connect the encoder ground to Arduino ground. Or let's look at the schematics. This wire over here should be connected to the Arduino ground. And that's it. To be able to develop the code that will interface the encoder with Arduino, it's first very important to understand the working principle of the encoder. For that purpose, I attached my DC motor to the power supply and I let the DC motor to spin in one direction, in particular in the clockwise direction. Then, I attached an oscilloscope probe to phase A as well as to phase B. That is, I have two oscilloscope probes that are attached to both phase A and phase B. And as the motor is rotating, our encoder is detecting these pulses. This yellow train of pulses represents the phase A, and this blue or light green train of pulses represents the phase B. And this is the situation when the shaft of the motor rotates in a clockwise direction. You can see that phase B leads phase A. Then, here's the situation when the motor shaft rotates clockwise. That is, rotates in the opposite direction. And again, you can see phase A, the yellow line, and you can see the phase B, the blue line. Over here, you can see that now the phase A leads phase B. Later on in this video tutorial, I will explain how these two graphs can be used to develop the code. Okay, let's start with code development. Over here, you can see the final code. You can see the main sketch or Arduino file. And over here, you can see the C++ header file as well as the C++ implementation file. You can see that my files contain a lot of comments explaining the purpose of every function and every member variable, and my suggestion is to adopt this coding practice. That is, to always write comments before your functions explaining what the functions are doing. And you should do that in the header file as well as in the main file. Also, if you have more time and more energy, you can also comment the implementation file. Now, in the sequel, I will explain how to develop this code from scratch, and I will not write comments. I will also provide a link to these code files in the description below this video. Okay, let's start with the implementation. First of all, open Arduino and start a new sketch by clicking on File and New Sketch. And over here, let's save this sketch. Click on File and click on Save and save it in your default folder. Here it is. The first step is to develop the header file of our class. So click here and click on New tab, and let's name this header file. I will call the header file as encoder class.h. Here it is. Next, let's define guards. If not def, that is if not defined, and then type everything with capital letters, encoder class underscore h, then type define encoder class underscore h. Everything should be capital, and then complete the guards by just typing and if. So what are the guards? Namely, in our main sketch, we will include this header file. However, it might happen that in some header file or in some other sketch or anywhere else, you include encoder class file several times, or you include a file that again includes a header file, encoder class. And this will create issues since compiler will complain that you're redefining the class. That's why we are including these guards. These guards are telling to the compiler, if not defined encoder class, define the encoder class. Or if you didn't see before the encoder class, define the encoder class. Next time, for example, encoder class is included, it's not going to be included in the main file because these guards will prevent redefining the class. Okay, so let's define our class. I will call the class as class encoder class. Here it's very important to make sure that the name of the class matches the name of the file. Okay, so let's start defining the class. Don't forget to start the class and to end the class like this. First of all, let's type public for public functions and private for private member variables. The private member variables are volatile, long, total pulses. This variable will be used to store the detected pulses, and over here we use long since we want to expand the storage capacity. Then we need to define our pins, so let's do that. Assign int pin encoder A and unsigned int pin encoder B. These two variables will store the encoder pins. That is one pin for the phase A and one pin for the phase B. Later on in the main file, we will define these pins, and these pins will be set by our constructor. Next, let's define our constructor. So copy and paste the name of the file, and over here we need to make sure that the data types correspond to the data types of the private member variables. So over here we will have unsigned int, and I will call it as pin A. Then we will have unsigned int pin B. And that's it. This is our constructor. Later on, we will implement this constructor. Briefly speaking, this constructor will set pin encoder A to be equal to pin A and pin encoder B to be equal to pin B. In this video tutorial, I will teach you how to detect pulses with high resolution and with low resolution. I'm doing this since low resolution is beneficial when your shaft is spinning relatively fast and when you don't care about the actual resolution, although the low resolution is probably still enough for most applications. On the other hand, I will also teach you how to measure the pulses with high resolution. However, high resolution is not suitable if your shaft is spinning very fast, since it's going to use more interrupt time and more digital read time. So let's define two interrupt functions, and I will explain later on the purpose of these interrupt functions. The first interrupt function will be used to measure the pulses with low resolution, and consequently I will call it count pulses low resolution. Then I will define another function that will count the pulses with high resolution. These two functions will be the interrupt functions, and they will be called every time a rising or a falling edge or both edges are detected by our encoder. The next step is to define a function for initializing the encoder. The function will be called init encoder, and over here I need to specify a pointer to a function, and I will explain the purpose of this pointer later on. Here I will type ISR underscore callback, and over here I will need to specify void. And over here I need to define an assigned integer that will additionally specify the resolution. Okay, and finally we need to define the function for retrieving the member variable total pulses and for printing it. Consequently, over here I need to make sure that the signature matches. Consequently, I need to type long get pulse count, and here it is. That's it. This function will simply return total pulses. Let's save this file and let's proceed. Before we define our implementation file, over here it's very important to add this statement. Include Arduino.h. Arduino.h is the standard Arduino header file that's actually automatically included in the main file. However, since we are using in this file as well as in the implementation file some built-in Arduino functions, over here we need to include Arduino.h, and this is very important. The next step is to define the implementation file. For that purpose, click here and click on New tab. And let's give the name to our implementation file. The name should be encoder class.cpp. And over here, it's very important to keep in mind the following. The name of the implementation file should match the name of the header file. The only difference should be in the extension. Here the extension is CPP, which means this is a C++ file, and click OK. And here it is. Again, make sure that the encoder class names are the same, and don't forget to add this include Arduino.h to the header file. Let's start with the implementation of our constructor. The constructor implementation is actually super simple. So let's use the names over here. Let's copy encoder class. Then let's type this. And over here, let's type encoder class. And let's make the signatures match by just copying this part over here. Here it is. The purpose of this constructor is to set the pins. So let's see the member variables and the total pulses. I have to correct myself. The purpose is not only to set the pins, the purpose is also to initialize the total pulses. So let's start with that. We say total pulses is equal to 0, since we are starting the measurement. Then over here, we need to say pin encoder A is actually equal to pin A. So let's do that. And over here, we have that pin encoder B should be equal to pin B. And that's it. Let's save this file and let's continue. The next step is to implement the interrupt function that will count pulses with low resolution. Consequently, let's copy this prototype and let's paste it in this implementation file, and let's fix a few things over here. Finally, after this void, you need to type this to make sure that this function is properly defined in the implementation file. And let's save this file and let's implement the function. This function will use a basic principle for detecting the pulses. Namely, it will count the pulses on every rising edge of phase A. Namely, over here, you can see two graphs that I previously explained. This is the situation when the main shaft of the motor rotates clockwise, and this is the situation when the main shaft of the motor rotates counterclockwise. So let's analyze the situation when the motor shaft rotates clockwise. We can see the phase A and we can see the phase B. We will count the pulses on every rising edge of phase A. That is, we will count the pulses over here, over here, over here, over here, etc. So what can be observed? First of all, when the rising edge of phase A is detected, the value of phase A goes to high. If we immediately do digital read of phase B, we will also observe high over here. That is, if we are rotating in clockwise, then after the rising edge of phase A is detected, phase A and phase B have the same high value, and this is very important. And you can see this is the case on every rising edge of phase A. Let's analyze the counterclockwise situation. So what happens in the case of counterclockwise? We have detected a rising edge of phase A by our interrupt. Then, if we immediately do digital read of phase B, we can see that the phase B is low. However, the phase A is high. Then again, if we detect the rising edge of phase A, and if we immediately do digital read of phase B, we can see that phase A is high and phase B is low. This means that if the value of phase A is not equal to the value of phase B on every rising edge, then we are rotating counterclockwise. And this is very important. If we are rotating clockwise, we will simply increase the value of pulses for 1. However, if we are rotating counterclockwise, we will simply decrease the value of total pulses. So let's implement that. Here it is. This function is called on every rising edge of phase. So let's write it here. This function is called on the rising edge of phase A. Later on in this tutorial, I will explain how to properly register this function such that this function is called on the rising edge of phase A. For the time being, this is not important, so let's simply implement the code. So let's write if digital read of, let's see now, pin encoder B. This is the pin that measures the phase B, is greater than 0, then what happens? We do the following. We simply increment total pulses for 1, and that's it. Let's analyze what's written over here. First of all, we are using digital read function. This digital read function is not defined in our implementation. It's actually defined in Arduino.h. That's why we have to include Arduino.h over here. Now, to use this implementation file, on top of this file, we need to type this, include encoder class H. And this is very important. Otherwise, the code will not work. That's why we need to do this, and that's why we need to basically keep in mind that the definitions are defined over here. So don't forget this step over here. Otherwise, the code will not work. To emphasize again, over here we are calling the standard Arduino function digital read, and this function is defined in Arduino.h. There will be no problems for calling this function inside of this file, mainly because we are including encoder class.h, and encoder class.h includes Arduino.h, and this is very important. So if digital read pin encoder B is greater than 0, we know that phase B is greater than 0, that is, the phase B is equal to phase A, since the phase A is already high, and that's why we increase the pulses. Otherwise, what do? We simply decrease the pulses. And that's it. This first case over here covers this graph, and this case over here covers this graph, and we are all set. Here I have to mention this. This function will be called on every rising edge, and it implicitly means that the value of phase A is already high, or it's greater than 0. That's why this digital read greater than 0 is a substitute for a statement if digital read pin encoder B is equal to digital read pin encoder A. However, we don't need to do digital read of pin encoder A, since this function is called actually on the rising edge. That is, it's called when phase A already becomes equal to high, and this is very important. Okay, let's continue with the implementation of the second function. And here is the second function, count pulses with a high resolution. And over here, I will scroll down and I will show you the second case. But before we implement the second case, let's simply copy this prototype and let's paste it over here. And let's fix a few things. And let's make sure that this function is properly implemented. Here it is. So let's analyze this case. In this case, we will detect pulses, or better to say, we will measure the pulses on both the rising and the fall edges of phase A. And in that way, we are going to increase the resolution or the measurement accuracy. Consequently, this function over here is called on every rising and fall edges of phase A. If our shaft is rotating clockwise, you will have this situation. And let's analyze what's happening over here. Over here, the rising edge is detected, and if we immediately do digital read of phase B, we will see that the phase B is high. That is, both phase A and phase B are high. Next, if you go further, then again, fall edge of A is detected, and if you immediately detect phase B or do digital read of phase B, we will observe that the value of phase B is actually equal to the value of phase A. This is because phase A felt too low, and over here phase B was already low. Then again, if we detect the rising edge of phase A is high, and if we measure phase B, it's also high, so the values are equal. The same thing happens here when we detect the fall edge. Phase A goes to 0, and if we measure phase B, it's also low, and again the phase A is equal to phase B. Consequently, if phase A is equal to phase B, this means that we are rotating clockwise. On the other hand, let's see what happens when we rotate counterclockwise, and here's the situation. We call this function on every rising or fall edges of phase A. Over here, the rise edge is detected and phase A is high. If we immediately detect phase B, it will be low. The value of phase A is different than the value of phase B. If you go further, we are detecting the fall edge of phase A, and if we immediately do digital read of phase B, we will see that phase A is low and phase B is high. That is, if we are moving counterclockwise, the value of phase A will not be equal to the value of phase B, or other way around, if the value of phase A is not equal to the value of phase B, we are moving counterclockwise. Okay, so let's write a function that will count the pulses by using this principle. The function is relatively simple again. So what's the principle over here? Let's type if. Then inside of this if statement, let's do digital read again. And over here, I will read pin encoder B. Let me copy the value. And if this value is not equal to the digital read, pin encoder A, then over here we need to increment or decrement the pulses. In fact, it's completely your choice. Are you going to increment or decrement the pulses on the clockwise, on the counterclockwise rotation? However, let's use this principle. If this is the case, this means that we are moving the counterclockwise, and consequently, let's decrease the pulses over here. Although it doesn't really matter, since this is just a convention. Consequently, let's repeat again. Over here, we have the counterclockwise situation, and phase A value is not equal to phase B. Over here, we perform the test. If phase B is not equal to phase A, then decrement. Otherwise, you will have this situation. Phase A will be equal to phase B, and we will actually need to increment, and that's it. Simple as that. Of course, you can do a number of variations about revolving around this example, and you can improve this code. However, in the interest of time, I presented the simplest possible implementation of these two functions. Next, we need to implement this function. The purpose of this function is twofold. First of all, this function will register pin encoder A and pin encoder B as input pins. That is, it will tell to Arduino that we want to receive information or digital reads from pin encoder A and pin encoder B. Secondly, this function should register count pulses low resolution and count pulses high resolution as interrupt functions. So let's start with the implementation of this function. Over here, to save time, I'm simply going to paste the content of this function. Consequently, you first need to write this, and let's explain what are the input parameters of this function. The first input parameter is actually a pointer to the interrupt function. Namely, outside of this function and outside of the class, the user will call on the init encoder on newly created object, and it should specify the name of the interrupt function. The name of the interrupt function should be either count pulses low resolution if you want to perform low resolution measurement, or count pulses high resolution if you want to perform high resolution measurements. In addition to this, the user should explicitly specify is it a low resolution or a high resolution by specifying this integer. If you want to have high resolution, you need to say resolution encoder is 1. Otherwise, if you want to have high resolution, 2. Or let me correct myself, for low resolution you need 1, and for high resolution you need 2. Inside of the function, first of all, we need to register pin encoder A and pin encoder B as digital input pins. To do that, we need to use this built-in function pin mode. Again, we didn't define pin mode inside of this implementation file. We can use this pin mode function since in the header file we have included arduino.h, and inside of our implementation file we have included our header file, and consequently we have implicitly included arduino.h, and we can use all the built-in functions including this function. Okay, the next step is to properly register our interrupt function. If resolution encoder is equal to 1, this means low resolution, and we need to register the first function. To do that, we need to use the built-in Arduino function called attach interrupt. First of all, we need to specify the pin that we want to attach interrupt to. For that purpose, we are using digital pin to interrupt function, and we are specifying the pin encoder A. That is, we are attaching the interrupt to the phase A, or to the pin encoder A. Then over here, we are specifying the pointer to the ISR callback, that is to our callback function. And over here, we are telling to Arduino, register this pin and this function, and let the function be called on every rising edge of phase A. And that's it. Okay. In the case of high resolution, we again need to repeat this. Again, we need to call digital pin interrupt. We need to specify the pin encoder A as a pin. Then here's the pointer to the interrupt function, and over here we need to specify change. This means that the interrupt function specified by this pointer over here will be called on both the rising and the fall edge of phase A. That is, on both rising and fall edges of the signal detected on pin encoder A. And that's it. Simple as that. Finally, let's go to our header file and let's implement this function. This function will simply return the total number of pulses. So here it is. Let's fix the implementation. Here it is. And over here, we simply need to return total pulses. So let's type here, return total pulses, and that's it. Let's save this file and let's continue. Again, don't forget to save the implementation file, then don't forget to save the header file, and let's go to our main file. The first step is to define the pins. Over here I'm typing define encoder A2. This means that this name encoder A is actually 2, and if you go back to my diagram over here, that is to the wiring diagram, you'll see that the phase A is attached to the pin number 2. That's why over here I'm typing encoder A2. Encoder B phase is attached to the pin 7 of my Arduino, and consequently over here I'm typing 7. Then I'm including encoder class.h, and this is all you need to do in order to use this class. That is, you don't need to include the implementation file, you only need to include the header file. Let's create our encoder object and let's return a pointer to that encoder object. So let's type new encoder class, and let's specify encoder A and encoder B. And that's it. That's our constructor. This statement, new encoder class, will create an encoder object and it will return a pointer to the encoder object. So let's store this pointer like this, and let's call it as encoder 1. Here it is. Perfect. Let's save this and let's continue. Now, inside of our void setup function, we need to do several things. First of all, let's do serial begin, since I want to print the encoder readings on my serial monitor, and let's specify the baud rate. Over here, I like to specify the max baud rate or relatively high baud rate. The next step is to call our function init encoder. So let's see over here our init encoder function. To call this function, we need to specify a pointer to the interrupt function, and we need to specify the type of resolution. So let's do that. And over here, I will type this, encoder 1. Then you need to type this, since encoder 1 is a pointer, and you cannot use a dot operation. You need to use this operator, and then you need to call the function init encoder. Here it is. And look what I will do right now. I will use lambda functions. That is, I need to type this, and inside I need to type this, encoder 1. Then I need to use this symbol, since encoder 1 is a pointer, and I need to specify the name of the function. Since I want to use low resolution, I need to specify the name of this function. And here it is. Simple as that. And then I need to specify 1, since I'm using a low resolution. So let's explain this. What you can see over here is a lambda function. I don't have enough time in this tutorial to explain what are lambda functions. However, this trick over here will pass a pointer to count pulses low resolution function. Then if you look inside of the implementation, over here, this pointer will actually point to count pulses low resolution, and it will properly register over here that this function, that is the count pulses low resolution, should be called and should be registered as the interrupt function, and it should be called on the rising edge. Simple as that. Nothing special. Then here's the statement, and this is performed only once. That is, the setup function is called only once. That is when we upload the code or if you reset your Arduino. After that, it's not being called. And this is all you need to do, basically. Simple as that. Then over here in the void loop, we will simply type this serial dot print line, And we will do this. We will call encoder 1, and we will simply call the function get pulse count to retrieve the pulses. And that's it. You can see how the code is simplified. This is the power of object-oriented programming. All the complexity is placed inside of the header file and inside of the implementation file, and your main sketch looks very simple. Before we can compile this file, let's make sure that our board is properly selected. Click on Tools, click on Communication Port, make sure that the communication port is selected, and make sure that the board is properly selected. That's it. Let's compile this code locally, and let's hope that there will be no errors. No errors over here, which is very good. And then let's upload this code. Now I'm uploading the code. Done uploading. Nothing is seen over here. To see something, you need to click on Tools, and over here you need to click on Serial Monitor. And over here you can see 000. Now I will pick up my motor and I will start rotating the shaft. And here I'm rotating. Let me go back. Let me go back to 0. Here I'm to 0. And let me try to rotate for 360 degrees. And let's see where I will go. Somewhere around 339 or whatever. Around 320 or 330. Now let's go back to 0. Let's go back. And I can see that I can accurately detect one full revolution forward and backward. This means that this function is working. That is, the low resolution detection of pulses is working. Of course, you can modify this code to perform angle measurements. Namely, you need to calibrate your encoder. Maybe you will buy, for example, a DC motor that will come with an encoder with more data on how many pulses you have per one revolution, and then through that you can actually detect the angle. If you don't have this information, and I don't have this information, you can perform simple calibration. Namely, you can rotate several times for 360 degrees, and you can measure the pulse number, and then you know how much pulses you have in 360 degrees, and you can divide 360 degrees per pulses to get degrees per pulse, and through that you can actually measure the angle. And then you can also measure the angular velocity by using the time function. I will explain this later on in this series. Next, let's test the second function, that is, let's test the count pulses high resolution. So over here I will comment this line, then I will copy this line, then I will simply paste this line, and I will change over here high resolution, and I will change 2 over here, save. Let's locally compile, let's upload, and let's see the outcome. Again 0, and let me now try to rotate for 360 degrees, and let's see, and we can see that the resolution is doubled. Now we are around somewhere 650, 60. This means that the resolution is doubled. This is because we are detecting on both the rising and fall edges. And that's it. Code works perfectly. Again, I will provide links to this manual over here that contains a very detailed information and basic principles for detecting the pulses. And I will also provide links to these code files. Okay, that's all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons, and see you in the next video tutorial.